If you're sitting on a C or a B in Edexcel AS Maths right now, and you're chasing that grade A, and kinematics is that one section of mechanics that is just stressing you out and nicking those marks from you, I need you to listen to this very carefully. Because the reason you're losing marks isn't because your maths is bad. Your maths is probably fine, and that's probably why you're sitting at a B at the moment. The reason you're losing marks is because you're probably answering a completely different question to the one the examiner asked you in the first place. And I know that because I used to do the exact same thing. So in the next 16 to 17 minutes, I'm going to be taking you through every core principle of constant acceleration in one dimension. Definitions, motion graphs, SUVAT especially. I'm going to walk you through a full exam style question that a student in my community was struggling with and show you exactly how a tough question that has so many moving parts can be broken down once you really understand the core principles and what you're looking for. This is the kind of question where the maths itself is GCSE level, but the wording is designed to scramble your brain and leave you chasing a bunch of loose ends. This is part one of a two-part series. Part two is going to close out the rest of the spec, but part one, this video, is going to give you the core principles and ironclad foundation that you need to lock in 80% of the marks that you'll need to for kinematics. So let's get into it. Quick thing about me first. I used to fumble kinematics questions all the time, a lot. And it wasn't because the maths itself was actually hard. The key thing was that the questions to me seem so subjective that I can never really figure out what exactly I had to do to solve the problem. But obviously the equations were extremely easy, but the key thing was the interpretation of the questions and trying to figure out what exactly the examiner wanted. So for instance, velocity instead of speed, displacement instead of distance, forgetting to flip the sign of g, and the most glaring of all is picking the wrong SUVAT equation because it felt right as opposed to the one that actually fitted the variables that I had. After really digging into these questions and getting to grips with the principles behind it, I started to realize that students who do well in these types of questions, they're not necessarily more mathematically inclined than you. But what they do have is the ability to easily and efficiently identify what exactly the examiner wants and how to strip down the question to its core components. And there are essentially three core components that you need to answer nearly every single SUVAT question. Okay? And I'm going to plant them now, and as you'll see through the questions we go through, we're going to be coming back to these again and again and again. Number one is to read what the question is actually asking for. So speed and velocity are not the same. Distance and displacement are not the same. If you mix those up, you've already lost the marks before you've started. Two is to pick a positive direction at the start of the problem and stick with it. You can't change your mind halfway through. And number three is to identify the absent variable before you pick a SUVAT equation. Okay, because once you do this, the right equation falls out automatically. So let's just refine some key definitions, otherwise everything falls apart. So everything in kinematics is either a scalar or a vector. A scalar means magnitude only, okay, something like speed, distance. A vector is when you have magnitude and direction. So for instance, acceleration, velocity, displacement. Okay, now what these definitions unlock for you in an exam setting is the ability to basically see, okay, when I start the question, which way am I going in terms of positive direction and which way am I going in terms of negative direction? So you need to decide, is right positive or is left positive? Is up positive or is down positive? And once you pick this direction, you need to stick to it. Okay, this is especially true when it comes to gravity questions. And the reason is for that is that basically you could do all the maths correctly, but because you didn't take note of the directions, you could end up with a completely different answer. Okay, so this is very important. Okay, so another key piece of foundational content relates to motion graphs. Okay, and there are 4 graphs that you basically need to understand and be able to work with. Okay, and in part 2 we'll be going through exactly how you can derive the SUVAT equations from these graphs. But for now, let's just go through each graph and how to interpret them. Okay, so displacement time graph. We have S on the y-axis and T on the x-axis. Here, the gradient, which is the slope, that gives you velocity. So we have a steep line, that means a faster object. When we have a horizontal line, that means the object is at rest. And a negative gradient means that the object is coming back. Okay, now velocity time graphs is where a lot of students get killed, because here we have two readings. Okay, we have gradient, which gives you acceleration, and area under the graph, which gives you displacement. So you have two completely different things on the same graph. Okay, so if they ask for acceleration, you find the slope. If they ask for displacement, you find the area. And watch out for this key trap. Okay, if part of the graph is below the t-axis, what does that area count as? Well, that area counts as negative displacement. So your total displacement is the area above minus the area below. Now, speed time graphs. These look similar to velocity time graphs, but anything that would have gone below the axis now gets reflected upwards. It's, in a way, you can make an analogy to absolute value graphs, okay? Because here, speed can never be negative. So the area under a speed time graph gives you distance traveled, not displacement, but distance. Acceleration time graphs are pretty rare, but essentially they look like this, and the area under it gives you change in velocity. Okay, now onto SUVAT. Here we have 5 equations that only work when acceleration is constant, which in the context of your AS paper is basically all the time, unless they tell you otherwise. The 5 letters, they stand for things you might want to know or want. So that is S, displacement, U, initial velocity, V, final velocity, A, acceleration, and T, time. Now the 5 SUVAT equations that make use of these variables, and remember we'll derive these in part 2, but for now you just need to know how to use them. The first is V is equal to U plus AT. The second is S is equal to UT plus half AT squared. The third is S is equal to VT minus half AT squared. The fourth is V squared is equal to U squared plus 2AS. And the fifth is S is equal to a half U plus V times T. Now what you'll notice is that in each of those equations, there is an absent variable. Now, what's the point in these? Well, the point in these is that every kinematics question is going to give you, whether in the beginning or what you get to later in the question via working out, is 3 of those 5 values. Okay? And you're going to be asked for a 4th. So that means there's always a 5th value, one that isn't given and isn't being asked for. And that's your absent variable. So you don't pick a SUVAT equation just by what you feel is right. You pick it by looking at which variable is missing and choosing an equation that doesn't contain it. So if the question gives you U, A, and T, but asks for S, the absent variable is V, so we're going to use equation 2. And if the question gives you U, V, S, and asks for T, then the absent variable is A. So that's the entire skill. You need to identify the absent variable, pick the equation that ignores it, and then plug in and solve. So where I was going wrong before was I used to skip this step entirely and just try to remember which equation I'd seen on the last past paper or whatnot, and what variables I had, and just try to figure out something that worked. Okay, just try, throw an equation at the wall and see which one sticks with the variables given. But once I became a lot more systematic with it and realizing which one was absent, that changed everything, because now I had a system for trying to work out, okay, this is the right equation I need to use. So what I'm going to go through now is a hard type of question, okay, that you'll see in a kinematics question that it's not easy, it's not intuitive, but you really have to understand the principles to get to the answer. And this is the same question that the student came to me with, because they're doing really well, and even this was tripping them up. So they asked for some help on this. Okay, so let's go through it together. A cat starts running from a point O along a straight horizontal path with a constant speed of 4 meters per second. 2 seconds later, a dog starts chasing the cat from the same point, O. The dog accelerates uniformly from rest for t seconds until it reaches a speed of 6 meters per second. Then the dog continues at a constant speed of 6 meters per second. The dog then catches the cat 12 seconds after the cat started running. Now again, the reason why students would struggle with this question is not because the maths itself is difficult, it's because you look at this question and there's so much going on. But when we break it down, what actually is going on is that we have two timelines. We have the cat's timeline and we have the dog's timeline. Now the first thing you want to do in a situation like this is anchor everything to one clock, to one timeline. So what I did was I set t is equal to 0 at the moment the cat starts running. Okay, and everything from now on is cat time. And then the dog starts at t equals 2. The catch happens at t equals 12. So therefore we have a complete timeline that encompasses both the cat and the dog, and we can clearly see the split between cat time and dog plus cat time. Now part A says to find the distance of the cat from O when the dog starts running. So this is where it gets really interesting, because here the cat has been running at 4 meters per second for 2 seconds. Remember, the cat is running at a constant speed throughout the entire timeline. So here we don't even need SUVAT. We can simply say that distance is equal to speed times time. So that's 4 times 2 is equal to 8. 8 meters. Okay, so this is a question where you can easily model things up, overthink it, but it's actually quite simple. Now for part B, it says to find t. Now this is where the real money is, and this is where my student was especially finding difficulty. The trick here is to use the timeline as a whole and make use of the fact that the cat is running at a constant speed. Because when we're running at a constant speed, okay, that makes the whole variable finding process a lot easier, because if we have t and we have v, we can find s. So where is the cat at t is equal to 12? Well, the cat, remember, runs at a constant 4 meters per second for the full 12 seconds. So the cat is at 4 times 12, 48 meters from O. Where is the dog at t is equal to 12? Well, the dog also has to be at 48 meters because it just caught the cat. They're at the same point. How long has the dog been running by t is equal to 12? Well, that's 12 minus 2, which equals 10 seconds. Now, if we split those 10 seconds into 2 phases, the first t seconds, the dog accelerates from rest to 6 meters per second. After that, the dog runs at a constant 6 meters per second for the remaining 10 minus t seconds. Okay, so now we have split our question into 2 phases, okay? At least for the dog. Okay, so we have phase 1, which is the acceleration phase. So for this phase, okay, and it's different from phase 2, the dog is accelerating. Okay, so we're going to list out our SUVAT variables, and we're going to say to ourselves, do we know S? We don't know S. Do we know U? We do. That is 0, because we were told that in the question. Do we know V? Well, we know we get up to 6 meters per second, so yes, V is our final velocity. Do we know A? We don't know A. Do we know T? We know T is equal to capital T. Okay, so technically we have 3 unknowns, but I'm going to pretend we know T because it's going to help us solve the greater equation altogether, right? If we take a look here, which variable is neither needed nor required? Well, that variable is A. We don't need that. But what we are looking for is S, because that's going to help us solve the grander equation combining with the cat's velocity as well. So what that gives me then is S is equal to a half U plus V times T, because this equation avoids A, which means that our displacement for the first phase is equal to a half 0 plus 6 times T, which gives us S1 is equal to 3T. Now for phase 2, for the dog, this is quite interesting because here we don't even need a SUVAT equation. What I can simply say here is if we list out our SUVAT equation variables, S we don't know, U we know is equal to 6 because remember it's constant speed, we started at 6, so it's it's going to remain constant. V is 6 for the same reason. Okay, we're not changing that. And because we're traveling at a constant speed, A is 0, we're not accelerating. And we know that our t is going to equal 10 minus t. Well, this is interesting because remember, if we're traveling at a constant speed, we can just use V is equal to S over t. Okay, which means that S is equal to V times t, so S2 is equal to 6, 10 minus t. Okay, so that's going to be our value for S2. Now, what do you remember from the start? The final dog distance is going to equal the final cat distance. So S1 plus S2 for the dog is going to equal the cat's total distance, which means that 3t plus 6 times 10 minus t is equal to 48. So simplifying this out, we get negative 3t is equal to negative 12, which means that t is going to equal 4 seconds. Now for part C, it wants us to find the acceleration of the dog. Now obviously we know that the dog is only accelerating in phase 1. So if the dog's only accelerating in phase 1, if we list out our SUVAT variables, okay, we know that S is equal to 12 because we're simply going to plug in t is equal to 4. We know U is 0 because we start from rest. We know V is equal to 6. A we don't know, we know t is equal to 4. Okay, so here we've got a pick of the litter when it comes to equations. Okay, we're trying to find A, so really we could use a few equations. We can use V is equal to U plus AT, or V squared is equal to U squared plus 2AS. But what I'm going to use here is just V is equal to U plus AT. So plug in our variables and we get A is equal to 1.5 meters per second to the negative 2. So now when it comes to drawing a graph, a VT graph which they want, how do we go about doing that in a way that guarantees us full marks? There's one key thing that you need to remember when it comes to SUVAT equations. When we are trying to find those variables out, we think of time as the interval, okay? So for instance, t, 10 minus t. But when it comes to drawing graphs, we care about the time stamp. So here, because we're drawing a graph, we care about the time stamps. So our time stamps here are going to be 0, 2, 6, and 12. Okay, and we're going to work out the velocity at each one of those stamps. And we do that for the cat, well, that's just 4 across the board. For the dog, we're going to be at 0 right at the beginning, and 0 at t equals 2, because remember we start from rest. 6 meters per second at t is equal to 6, and 6 meters per second at t is equal to 12, because remember we stuck to that velocity. So now all we have to do is draw the graph according to these points. And when we do that, we get something like this. As you can see, the cat's velocity is just a straight line, straight horizontal line, ending at 12.4. Okay, meanwhile the dog follows a slightly different trajectory. We got a straight horizontal from 0 to 2. Okay, then we got a constant acceleration from 2 to 6 seconds, and then we've got a constant velocity from 6 to 12 seconds. Okay, so the key thing to remember about graphs is that you don't have to be an artist, you don't have to draw everything to minute scale. As long as you get the key points there and the key shape there, and you label basically everything, okay, that you need to label, so intercepts, axis, key points, etc., you'll be fine. Again, also asymptotes when it comes to pure, but that's a different subject altogether. But as long as you do that, you'll be fine. Don't overthink it. Okay, now this is a question that pops up a lot, especially in Excel. It says, state a limitation of the model. Well, this is just testing your understanding of, the actual physics that we're doing here. And there's a wide variety of different things you can say here. What I find easiest to say is something like, well, animals don't move at constant velocities. And also, both are treated as particles, ignoring their size, right? So you just need to figure out what reality actually looks like and try to compare that to, the situation that we've modeled. So the classic one, when it comes to, say, like an object in the air, falling is like air resistance, for example. Okay, we don't at least at this level encompass air resistance. whereas in reality you obviously do. Now, speaking of gravity, how do we solve those questions where someone is falling or we're throwing something up in the air? How do we go about working out those questions? Well, the first thing we need to do is realize that acceleration has a fixed magnitude, and that is, at least for Edexcel, we're going to take g is equal to 9.8 meters per second squared. Most of the time though, they'll use 10 to make the maths cleaner. Just basically use whatever they tell you, okay? Now, gravity obviously always pulls downwards. So for instance, if we've got a ball going up in the air, gravity is going to be pushing against it. And what else happens when the ball goes up in the air? Well, as you can see, we start with initial velocity u, and our final velocity is always going to equal 0. Why? Because remember, if we get to the top of our trajectory before falling down, for that moment, we come to complete rest, okay? So we know that v is always going to equal 0 for these types of questions. Now, there's a classic mistake that a lot of people make, that rhymed quite well, but this is the classic mistake that often happens when it comes to these gravity type questions, and that is not getting the sign right. If we take up as positive, then gravity acts in the negative direction. So a is equal to negative g. Okay, so that's negative 9.8 or negative 10. And if you take downwards as positive, then a is equal to plus 9.8. Both work, but just don't chop and change midway through the question. Okay, so stick to one that works for you. Now, to make life easier for you, here are 4 key results that pop up when it comes to these types of questions that it's extremely helpful to memorize, but you don't necessarily have to memorize it, but they will come up again and again and again when you're doing the working out. Maximum height, okay, if we set v is equal to 0 in v squared is equal to u squared plus 2as, then our maximum height is always going to be u squared over 2g. Our time to that maximum height, okay, again, it's setting v is equal to 0 here, in v is equal to u plus a2, well, that's going to be u over g. And then total flight time back to launch, by virtue of symmetry, we can say that t, okay, our total t that is equal to 2u over g. And our speed on return to launch height, again by symmetry, that's going to equal u. So let's do a quick example, because obviously these principles are all airy-fairy until you actually put them into use. So let's say a ball is thrown vertically upwards from a height of 3 meters above the ground with a speed of u meters per second. It hits the ground 3 seconds after leaving the hand. Take g is equal to 10 and find u. So step 1 here is to pick a direction. So what I'm going to pick is g is equal to negative 10, because that just seems a lot more intuitive. Okay, so downwards is negative, upwards is positive. Step 2 is to list out the SUVAT variables. So for s, and this is an important point, s is going to equal minus 3, not plus 3, minus 3. Because think about it, it tells us that the ball hits the ground, okay? So our phase here, our scenario is the entire scenario, okay? We're not doing it in phases here. So as a result, we know that the ball ends up 3 meters below where it started. That's its total displacement. Remember, up is positive, down is negative, so that's minus 3. U, we're told that is capital U, so put that there. V, we don't know, and we don't need it, quite frankly. And a is minus 10, t is equal to 3. So v is obviously the absent variable here. And what do we do with absent variables? Well, we find the equation where v is simply just not included. So that is going to be s is equal to ut plus half at squared. And putting that all together, we get minus 3 is equal to 3u plus half negative 10 times 9, which when simplified, we get 3u is equal to 42, which means that u is equal to 14 meters per second. Now this is all well and good, but what are the key mistakes that you can watch out for to ensure that when you do these questions, and you obviously know all the theory now, what are those mistakes that you can watch out for so that they don't trip you up. Well, the first mistake is mistaking vectors and scalars. So for instance, you're answering velocity instead of speed when they want speed. So you need to just keep an eye out as to what exactly they want, draw the graph, or give the value that they want. Okay, even though velocity and speed are quite similar, you need to be very careful with that. And this leads me to the second mistake, which is sign convention drift. So if you pick direction, you have to stick to it. So if you pick down as negative, okay, so we have negative 9.8, don't change it. Okay, for that question, don't change it. And the third mistake, which in my opinion is probably the most critical, is trying to apply SUVAT to a multi-stage problem the same way as you would to a single stage problem. Okay, so for instance, a car accelerates, then it brakes. That's a 2 SUVAT stage question there. It's not one, because the final velocity of stage 1 becomes the initial velocity of stage 2. If you try to do it all in one go, you're going to get a very confusing answer. So what you need to do is draw a timeline and split the stages, and from there you'll be able to really understand the principles behind the motion in that graph, or in that question, sorry, and it'll make things a lot easier. Now what we have just covered is the core foundation. This will cover about 80% of everything you need to know in kinematics, but what if the examiner says to you that our acceleration is changing? Well, what do we do then? Well, that's going to be covered in part 2, where we're going to go through exactly what happens when that acceleration variable is changing, because that changes everything. And not only that, we'll be going through how to derive the SUVAT equations as well, which is something the examiners like to slot in as a difficult question. One more thing before we go. If you're keen to take your A-level maths to the next level and aim for an A-star like Fersen or Ben here, make sure to click the link below. We currently have 5 more free slots available on the platform, and once that's gone, we'll be switching over to paid. So if you're keen to get some free value there, make sure to click the link below and apply.